The first part of our lecture today is going to be continuing mass to moles to mass and limiting reactant problems. So here is a typical problem you might find in chemistry. A calcium nitrate sample contains 2.04 grams of nitrogen. How much does the calcium nitrate sample weigh? Now, from the previous lecture, you know that you're going to have to start with what you're given and then select some ratios that are 1 divided by 1 to get to the value that you're being asked for. So we're going to start with 2.04 grams of nitrogen, which is one material, and we need to get to grams of a different material. So how are we going to get there? It's going to take us 3 different ratios. Here's the challenge in chemistry, though. Which ratio of 1 divided by 1 do you use? Well, there are some ratios from the periodic table that give us the molar mass. Then there are ratios from within the chemical formula. For example, if you look at the formula, calcium nitrate has 1 mole of calcium per 1 mole of the entire compound, or 2 moles of nitrogen per 1 mole of the entire compound, or 6 moles of oxygen atoms for 1 mole of entire compound. There's even ratios within the compound. The ratio of calcium to nitrogen within the compound is 1 to 2. Or calcium to oxygen is 1 to 6, or nitrogen to oxygen is 2 to 6. And then, of course, we have the molar mass of the material for 1 mole of that same material. So there's 10 ratios to choose from. You only need 3. So how do we go about solving this problem? As with all chemistry problems, start with what you're given. 2.04 grams of nitrogen. Our job is to get to moles of nitrogen. So hopefully you realize that's going to involve dividing by the molar mass of 1 mole of nitrogen atoms. If we look that up on the periodic table, there's 14.007 grams of nitrogen per 1 mole of nitrogen. This will get us to moles of nitrogen. You notice that the way we've set up this ratio, the units cancel. Grams of nitrogen are gone. Our next job is to get from moles of nitrogen to moles of calcium nitrate. So for this, we're going to use the stoichiometric ratio. This is a true ratio of 1 divided by 1. For every 1 mole of calcium nitrate, there are 2 moles of nitrogen. You notice how the units cancel. We get rid of moles of nitrogen, and we now are to moles of calcium nitrate. Finally, we need to get from moles of calcium nitrate to grams of calcium nitrate. So we can use the molar mass for that. It is a true ratio of 1 divided by 1, that there are 164.086 grams of calcium nitrate in 1 mole of calcium nitrate. The units are going to cancel out, and we are left with units of grams of calcium nitrate. So when you punch this all into your calculator, you will discover that there are 11.9 grams of calcium nitrate. So let's take a look at these steps one last time in detail. If you look at this first ratio, you're actually dividing by the molecular weight. If you look at this second ratio, you're actually multiplying by some sort of stoichiometric ratio that you get from the compound or perhaps from a chemical reaction. If you look at this third ratio here, you're actually multiplying by the molecular weight of the new material. So that's how this works. So here's a question for you. A calcium nitrate sample contains 14.03 grams of oxygen. How many grams of nitrogen does it contain? I've got at the bottom the way to help you through this. So we're going to start out with our 14.03 grams of oxygen. And this refers to oxygen atoms within the compound. Remember that our first step is going to be to divide by the molecular weight. Our next step is going to be to multiply by the stoichiometric ratio. So within the compound, I hope you realize that there are 6 oxygens relative to 2 nitrogens. So you're going to have to take that into account. Finally, you're going to multiply by the molecular weight. The molecular weight of what? Well, of what you want. What do you want? Grams of nitrogen. So this is as simple as dividing by the molecular weight of oxygen, multiplying by the stoichiometric ratio, and then multiplying by the molecular weight of nitrogen. This next question is an interpretation question in chemistry because many students have had chemistry at a prior location and they realize that oxygen can mean 2 things. It can mean O, the atom, or it can mean O2, the molecule that we inhale. So how do you tell what the difference is? Well, typically, if you are working in a compound, like for example, our calcium nitrate, you want to use O, the atom. So that means the molecular mass is 16 grams per mole of oxygen atoms. If you are working with stoichiometry typically in a reaction, then you want to use O2, the molecule. So in terms of correct answers to this question, there's 3 of them. There is only one answer that is incorrect, and that is because the ratio is not 1 divided by 1. So as mentioned, this mass to moles to mass also works with reactions. This reaction has a particular stoichiometry. You need 4 moles of iron for every 3 moles of Cl2 to make 2 moles of iron 3 chloride. This question asks, how many grams of iron are needed to react with 75 grams of chlorine gas? Once again, we're going from grams of one material to grams of another. So we're going to need 3 ratios. We're going to start with 75.0 grams of Cl2. Our first job is to divide by the molecular weight to get to moles of Cl2. So I can either divide or I can take 1 over the molecular weight. Now, if you go and look up chlorine on the periodic table, 1 chlorine weighs 35.45. Notice that I have the correct mass for Cl2 because that is what I'm dealing with in the reaction. Not chlorine atom, chlorine molecule. My next job is to get from moles of chlorine to moles of iron. So you notice that we have stoichiometry in this reaction. The ratio of chlorine to iron is 3 to 4. So I'm going to cancel out my grams of chlorine and get to moles of chlorine. And now I'm going to make sure that when I use this stoichiometric ratio, that I put the iron on top and the chlorine on the bottom. This allows the units to cancel out. And I wouldn't want to put 3 moles of iron on top of 4 moles of chlorine. That is not the true ratio from the reaction. The 4 goes with the iron, the 3 goes with the chlorine. So now we have gotten ourselves to moles of iron. Finally, we can go to the periodic table and we can multiply by the molecular weight of a mole of iron atoms, which turns out to be 55.85 grams per mole. Notice the units have canceled out, and I am now to 78.8 grams of iron. So this is the entire series going from grams of one material to grams of another. What if the question had only asked you for moles of iron? Well, then just stop with two ratios. Now, many students are used to doing this stepwise. My only caution for doing that is make sure that you carry quite a few significant figures with your calculation to make sure you don't get errors from early rounding. So if you are more comfortable taking 75 grams of chlorine and first dividing it by the molecular weight to get the moles of chlorine, and then multiplying it by the stoichiometric ratio to get the moles of iron, and finally multiplying by the molecular weight to get the grams of iron, that's fine. Do it the way that works for you. So now, of course, we're to your question. We want to know how many grams of iron 3 chloride can be produced with 75 grams of chlorine and an excess of iron. All right, we are going to start as usual by taking our 75 grams of Cl2. What I recommend you do at this point is divide by the molecular weight of chlorine, multiply by some stoichiometric ratio. What would the stoichiometric ratio be? Well, we're looking at the ratio now between chlorine and iron 3 chloride. So that is the ratio that you would use. And finally, you would multiply by the molecular weight of my iron 3 chloride. So that is my suggestion for you in working this problem and coming up with the correct answer. One quick reminder that mass in has to equal mass out. The last two problems used 75 grams of chlorine. We required 78.8 grams of iron to react. And by now, of course, you've done that calculation for that question and come up with 153.8 grams of iron 3 chloride produced. Notice that our sum of masses for the reactants is equal to the mass of the product. Now we are to one of the more challenging problems for students in chemistry, that of the limiting reagent or limiting reactant. The idea is that you don't have a perfect stoichiometric ratio of 4 iron to 3 chlorine. So you're going to run out of one of these materials in trying to make your iron 3 chloride. One of your materials will be used completely and the other will be in excess. So how do you solve this problem? Well, starting with grams is not that helpful because that doesn't give you the ratio of the moles. So your first job is to divide by the molecular weight and determine the moles of the reagent. So I can use 55.85 for my iron, and when I divide the grams of iron by that value, I wind up with 4 moles of iron. For the chlorine, I am going to have to remember to use the mass for 2 chlorines. One is 35.5, so 2 chlorines in a Cl2 molecule would be 70.9. When I take 354.5 and divide by 70.9, I wind up with 5 moles. So at this point, this is deliberately an easy question setup, because I think you can see that if you have 4 moles of iron, you need 3 moles of chlorine, and you have 5 moles, so it's already easy to see that your chlorine is in excess, and your iron is going to be the one that you use up all of it. Another way to do this that works for Chem 101 is to think of this pictorially. So if I have 4 moles of iron, I am going to draw 4 gray spheres. If I have 5 moles of chlorine, I'm going to draw 5 orange dumbbells to represent my 5 moles of chlorine. Now I can think about making my product, which is Fe2Cl3. So I'm going to draw a circle around 2 irons and 3 chlorine spheres. That means I need to break a Cl2 molecule apart, but that's okay. That's what happens in reactions. We break bonds and we make new interactions. So I've made one circle. Can I make another circle containing 2 irons and 3 chlorine atoms? Yes, I can. I can make a second circle. Can I make a third circle? No, because I'm out of iron. So this circle method tells me my limiting reactant. Now, for those of you going on to Chemistry 201, which is the second semester, you're better off learning to do this method by what's known as ICE tables. In order to do your ICE table, first you determine your limiting reactant. So what you're going to do is divide each one of these molar amounts by its coefficient. So you notice a 4 in front of the iron, so I'm going to divide by 4. This tells me I can run the reaction one time. I have 5 moles of Cl2, but my coefficient is 3. So 5 divided by 3 tells me I can run this reaction 1.67 times. So my limiting reactant is going to be the one which allows me to run the reaction the least, which means the iron. All right, continuing with the idea of an ICE table. Those of you who are familiar with it know that you start with an initial row. Initially, I have 4 moles of iron, 5 moles of chlorine, and no moles of my product. Then you do what's called a delta row or change row. And what I want to do is subtract all the limiting reactant, which we have determined is the iron. So I'm going to subtract 4. Now on the delta row, everything is controlled by this first entry. The ratios have to be stoichiometric. So you notice in the reaction, we have 4 to 3 to 2. So if I subtract 4 moles of iron, I have to subtract 3 moles of chlorine. And I need to add 2 moles of Fe2Cl3. You notice that the reaction is going forward, so we subtract our reactants and we have a plus sign for our products. Our last row is called the final row, or as we get further into this class, the equilibrium row. And on the final row, we're going to tally the amounts in the initial and delta rows. So 4 minus 4 is 0. 5 minus 3 is 2. And 0 plus 2 is 2. So take a look at that for a minute. No moles of iron are left. 2 moles of Cl2 are left. 2 moles of iron 3 chloride are made. Does that work with what we got from the circle method? Let's check. Going back to this screen, we definitely have 0 moles of iron. There's absolutely no iron outside the circle. What about our Cl2? Well, let's think about this. There's one of them here, and if I put these two together, there's a second one. 2 moles of Cl2 are left over, which is precisely what we got using our ICE table. And finally, we have definitely 2 moles of our iron 3 chloride product. So the circle method should match the table method. So here is your question. We want to know how many moles of aluminium chloride can be made, and how many moles of aluminium are left over, and how many moles of chlorine are left over given these reaction amounts. 161.9 grams of aluminium and 425.4 grams of chlorine. We don't have enough space to work on this slide, so let's go to the next one. First things first, we're going to find the molar amounts of each material that we have. So if I take 161.9 and divide it by my 26.98, which is my mass of aluminium, I wind up with 6 moles. If I take my 425.4 grams and divide it by the mass of Cl2, so there's 2 of those, so I'm going to divide by 70.90, I also wind up with 6 moles. So first, let me do for you the circle method. I'm going to draw 6 circles to represent my aluminium. Now I need my Cl2. So I'm going to choose a different color just to distinguish it. There we go. Now I have 6 moles of Cl2. Now let me draw a circle making my product. Each product is 1 aluminium with 3 chlorines. So let me make a circle. Okay, I can make 1 mole. Can I make another one? Yeah, there's another circle. So there's another mole. So there's another mole. And there's another mole. So you see that I have made 4 circles. So I can make 4 moles of product. And I'm certain you can determine how much chlorine is left outside the circle and how much aluminium is left outside the circle. For those of you who like the ice table, let me get you started on that. Initially, I'm going to start with 6 moles, and 0. As far as my limiting reactant goes, I have 6 moles of aluminium divided by 2, so that means I can run the reaction 3 times. For the chlorine, I have 6 moles divided by 3, so that means I can run the reaction 2 times. So chlorine is my limiting reactant. So what I'm going to do is subtract 6. Remember, this first number governs the rest of the numbers that we have on our delta row. An easy way to explain this to you is to have you think about the operation that you did. In going from 3 to 6, you multiplied this by 2 and changed the sign to negative. So I recommend you do the same thing. 2 times 2 and made negative is going to give you a value there. 2 times 2, but this time positive, is going to give you a value here. And then you simply have to do simple math and you can complete the table. So I hope that helps you in understanding how to do a limiting reactant problem.